Good morning, life science students. Today we will be discussing aspirin, which is the last chapter of our curriculum. So sit back, relax, and enjoy the ride with me. Let's begin with the synthesis of aspirin. Aspirin has the systemic name or the IUPAC name of acetyl salicylic acid. Is synthesized by the esterification reaction between salicylic acid and ethanoic anhydride to produce aspirin and ethanoic acid. Ethanoic anhydride can be replaced with ethanol chloride in this reaction. The products in this case are aspirin and HCl. Remember, ethanoic anhydride and ethanol chloride are derivatives of ethanoic acid. What are the characteristics of such reaction involving the ethanoic anhydride or the ethanol chloride? The characteristics are fast, complete, and exothermic. Now, if the ethanoic anhydride is replaced with ethanoic acid in this reaction, the products will be aspirin and water, and the reaction becomes slow, limited, and athermic. Now let's look at the salicylic acid molecule. As you can see, guys, this molecule has two important functional groups. It has the carboxyl group, which is COH, and the hydroxyl group, which is DOH. These two groups have got to be located on carbon 1, carbon 2. Now the ring consists of 6 carbons and 4 H's, and inside the ring we have 3 alternating double bonds. These 3 alternating double bonds could be replaced by simply drawing a circle inside this ring. Ethanoic anhydride or acetic anhydride. Let's look at this humongous molecule. It has CH3 bonded to a carbon. This carbon is double bonded to an oxygen and single bonded to an oxygen. And the oxygen in turn is single bonded to a carbon, which in turn is double bonded to an oxygen. And of course we have CH3 on the right side. So as you can see, the functional group of the anhydride is simply designated by the triangle that we see. So anytime we have C double with an O, single with an O, then C double with an O, as you can see in the box, this is the functional group of the anhydride. Now the reason why we call it ethanoic anhydride is because it comes from ethanoic acid. And of course, we explained how we form the anhydride from the ethanoic acid in previous slides. So if you want to simply write down the condensed structural formula of the ethanoic anhydride, you can write it as CH3, then C double O, O, C double O, then CH3 on the right side. And like I said, sometimes they don't use the word ethanoic, they place instead acetic anhydride. Ethanoic anhydride and acetic anhydride both are the same molecule. Now we have to examine the aspirin molecule or the acetyl salicylic acid molecule. As you can see, guys, it's a humongous molecule. It has two important functional groups. It has a carboxyl group and an ester group. The carboxyl group, which is COOH, is simply denoted by the circle, and the group that we have in the square is the ester group. So please, this is the representation using the condensed structural formulas of aspirin or acetyl salicylic acid. This is the esterification reaction of aspirin using molecular formulas. C7H6O3, this is the molecular formula of salicylic acid. reacting with C4H6O3, which is ethanoic anhydride or acetic anhydride, producing C9H8O4, which is the molecular formula of aspirin, and C2H4O2, which is the molecular formula of ethanoic acid. This is the esterification reaction of aspirin using the condensed structural formulas. As you can see, the salicylic acid on the left is reacting with the acetic anhydride, producing the aspirin, which is acetyl salicylic acid, plus acetic acid or ethanoic acid is the byproduct. Now, during this reaction, ladies and gentlemen, one can see that the H of the OH, which is the hydroxyl group of the salicylic acid, is involved in this reaction. And of course, looking at the acetic anhydride, it splits into two molecules. One of the molecules will pick up the H from the salicylic acid to produce the acetic acid, and the other part of the acetic anhydride will simply bond to the oxygen, producing the aspirin, as you can see on the right side. I have to use my handwriting to explain the esterification reaction. As you can see, the top reaction, ladies and gentlemen, it shows the salicylic acid reacting with the ethanoic anhydride, producing the aspirin and ethanoic or acetic acid. As you can see, the hydroxyl group in this reaction is involved, so the H is simply lost from the OH, and during the reaction, the ethanoic anhydride splits into two pieces. One of them will just pick up the H from the OH to produce the ethanoic acid, and the other part of the ethanoic anhydride will simply attach itself to the oxygen, producing the aspirin. Now, instead of using the ethanoic anhydride in the middle reaction, we are just using the ethanoyl chloride. As one can see, during this reaction, the aspirin is produced, but we don't produce ethanoic acid. Instead, we produce HCl. During this process, also, the H is lost from the OH, and it picks up the Cl from the ethanoyl chloride to produce the HCl, and the CH3COO attaches to the oxygen, producing the aspirin molecule. The last equation shows that when we use the ethanoic acid with the salicylic acid to produce the aspirin plus water, and as you notice, ladies and gentlemen, the first two, they are fast, complete, and exothermic because we're using the derivatives. The last reaction is slow, incomplete, and athermic. Let's examine these two chemical reactions involving the aspirin. Now, as one can see, in both these reactions, we have the strong base sodium hydroxide represented by Na plus OH minus. In the first reaction, the type of this reaction is an acid base. In an acid base reaction, the carboxyl group of the aspirin is involved. As one can see, during this reaction, the carboxyl group loses the H, and the H is picked up by the OH minus to produce the H2O, and the Na plus will simply attach itself right next to the COO minus. So in an acid-base reaction, the aspirin is simply involved using only its carboxyl group. Now, in the saponification reaction, the aspirin reacts with the strong base, but in this case, it's ester group that is involved in the reaction. Look at the right side. The COH is intact. We did not touch the COH, but the ester group is involved. The CH3 is plucked off or removed, and it picks up the OH minus to produce the CH3OH, which is the alkyl methanol, and the Na plus simply attaches itself right next to the O COO-, and the produced product is the soap. So as you can see, the aspirin can be involved in an acid-base reaction or saponification reaction. To recap, when the aspirin is in an acid-base reaction, its carboxyl group is involved, while in the saponification reaction, its ester group is involved in the reaction with the strong base. This is another remarkable reaction to pass along to you guys. It is the esterification reaction between methanol, represented by CH3OH, and salicylic acid, represented by C6H4OHCOOH. Now, since it's an esterification reaction, the alcohol, which is CH3OH, loses the H, and we lose the OH from the carboxyl group of the salicylic acid, producing the H2O on the right, and we have this ester known as methyl salicylate, which is known as wintergreen. Now, an important note also to pass along to you guys: in the production of wintergreen, the carboxyl group of the salicylic acid is involved in the reaction, while in the production of aspirin, the hydroxyl group of the salicylic acid is involved. Now lastly, let's talk about the solubility of aspirin in different media. In acidic medium, aspirin is insoluble. In basic medium, it is soluble. In a neutral medium, it is slightly soluble. So as the pH increases, the solubility of aspirin also increases. This, ladies and gentlemen, concludes our program. Thank you so much for tolerating me. God bless, and I hope to see you soon.